What if Atlas were heading toward Jupiter? The question sounds exaggerated, almost uncomfortable, as if it touched a boundary between the possible and the improbable. But that is precisely why it works, because when an interstellar object enters the solar system, everything we thought was predictable becomes uncertain. 3I Atlas did not originate here. It comes from another star, from an environment we will never see up close. Its movements, its composition, and its behavior carry the story of a journey that began millions of years before humanity existed. Just imagining for a moment that its trajectory could align with Jupiter opens the door to an extreme scenario, a coincidence so precise that it would force every calculation, every piece of data, and every physical possibility to be re-examined, not as a fact, but as an exercise to understand how far science can go when facing a visitor that does not follow the usual rules. In this hypothesis, the interest does not arise from fear but from mystery. Jupiter is the guardian of the solar system, a giant whose gravity dominates an entire region of space, and around it orbit worlds that challenge everything we thought we knew about life. Hidden oceans, deep chemistry, internal energy, and something that breathes. So when we pose this question, we are not seeking a definitive answer, but an exploration. What would it mean for an interstellar object, by pure coincidence, to cross the gravitational domain of Jupiter? What real processes would come into play? How would astronomers react? This, and yes, does not announce danger or destiny, but an opportunity to observe science with different eyes. Before we dive deeper into what would happen if 3I Atlas were heading toward Jupiter, there are 3 things you need to do right now so this scientific hypothesis reaches more people and the astronomical community goes into full alert mode. First, hit that like button right now so YouTube's algorithm pushes this hypothetical scenario to more observatories, researchers, and astronomy lovers around the world. Second, subscribe and turn on the notification bell so you don't miss any real-time updates on 3I Atlas, the latest actual observations and the new orbital calculations as they come in. And third, scroll down to the comments right now and simply write Jupiter to join the global registry of everyone following this historic interstellar object and this unprecedented scientific exploration. Do it now, don't wait. Science moves fast and this visitor isn't going to hang around. Let us imagine a hypothetical scenario. A newly discovered interstellar object, 3I Atlas, crosses the sky at a speed that defies everything familiar. In reality, its trajectory is hyperbolic and poses no threat. But in this theoretical exercise we ask ourselves what would happen if the calculations showed an unexpected alignment heading toward Jupiter. This is not about predicting or announcing anything, but about using this possibility to understand how orbits are studied, how non-gravitational accelerations work, and why a giant planet can completely change the fate of everything that passes near it. Science advances by asking itself the improbable. A small change in gas release, a minimal variation in brightness, a mathematical adjustment after new observations. Any detail can alter the interpretation of a trajectory. That is why, if an interstellar object showed an extremely precise coincidence in the direction of Jupiter, even if only as a hypothesis, astronomers would be forced to examine the phenomenon carefully. Jupiter has the real ability to deflect, slow down, or accelerate objects that approach it, and it also hosts moons that could hide environments where complex chemistry evolves without rest. In this hypothetical story we start from a completely real moment, the detection of 3I Atlas in July of 2025. That dawn, when the automatic system of the Atlas project marked a faint point moving among the stars, no one imagined it would become the third interstellar visitor identified by humanity. Its brightness was dim, its trail printed a fast curve, and its behavior matched what was expected for an object that does not belong to our solar system. The first calculations showed an almost perfect hyperbolic orbit, the mathematical signature of a traveler that enters, passes, and leaves forever. So far everything within known physics. But in this hypothetical scenario, what transforms the story is not the detection, but the question. What would happen if, as observations accumulated, an extremely precise coincidence emerged heading toward Jupiter? In real life, astronomers analyze every new image to refine the orbit. Each datum reduces uncertainty, as if thousands of tiny invisible threads adjusted the exact curve of the movement. In our exercise, that refinement gradually reveals something unexpected. The projected trajectory, under certain theoretical conditions of non-gravitational acceleration, would appear to approach significantly the gravitational domain of the Jovian giant toward the middle of March 2026. This is not about claiming that this is happening but about exploring how science and mathematics would begin to suggest a statistically rare alignment. In orbital dynamics, such a coincidence does not imply intention or destiny, but rather an extraordinary opportunity to study phenomena that rarely coincide in time and space. As this hypothetical projection becomes clearer, researchers imagine how they would react if an interstellar object appeared to coincide with Jupiter within a distance of tens of millions of kilometers. That separation is still enormous, but in celestial dynamics it is enough to activate scientific interest. Jupiter is a massive source of gravity, a dynamic core that profoundly affects everything that passes near it. Its influence can alter trajectories, modify velocities, and create temporary interactions with its magnetosphere. Thinking about an interstellar visitor approaching that environment, even if only as a theoretical exercise, opens the door to an avalanche of real questions. How would numerical models respond? What kind of perturbations would appear? What signals would astronomers look for? In this first part, the analysis also focuses on the natural behavior of icy objects. An interstellar visitor, as it approaches the Sun, begins to release gas progressively. Ice that had been frozen for millions of years sublimates for the first time, forming jets that push the object in a gentle but measurable way. In most comets, these jets produce chaotic accelerations that are difficult to predict. In this hypothetical scenario, the scientific question would be, what would happen if the jets were not completely random and, within the possibilities of physics, generated a tiny but sustained modification in the trajectory? Not because the object wants to go to Jupiter, but because physics theoretically allows a sufficiently persistent pattern of gas expulsion to deflect an orbit in an unexpected direction. Real science has documented non-gravitational accelerations in comets. So the question here is not whether it is possible, but what an extreme case would look like while still being based on known physics. This line of analysis inevitably leads to Jupiter and its moons. In our theoretical scenario, a relative approach to the planet would allow us to study how the Jovian magnetosphere temporarily captures particles, how dust grains are distributed, and how in theory they could interact with the icy surface of worlds like Europa and Callisto. These moons have been studied for decades because of their enormous astrobiological potential. Beneath their layers of ice lie liquid oceans heated by tidal forces, environments where chemistry could evolve in ways we do not yet fully understand. Thinking about an interstellar object approaching the environment of these moons, even if only as a hypothetical coincidence, poses an ideal scenario to explain what data an astronomer would look for, what instruments would be useful, and what information could be extracted about the visitor's composition. The mystery then arises not from the idea of intention, but from precision. In astronomy, when a trajectory coincides with another region of space in an exceptionally fine-tuned way, even without direct interaction, the scientific community pays attention, not because there is a hidden meaning, but because improbable encounters reveal deep dynamics. In this scenario, the hypothetical alignment with Jupiter becomes a natural laboratory for analyzing how an interstellar object changes when facing such an extreme environment. The intensity of radiation, the rise in temperature, accelerated outgassing, potential fragmentation, and interaction with magnetic fields are processes that can be studied without the encounter being real. Each one illuminates an aspect of physics that we normally cannot observe under such controlled conditions. This part 1 thus establishes the heart of the scenario: a real interstellar visitor, an initially simple trajectory, a hypothetical refinement that suggests a notable statistical coincidence, and a theoretical approach to Jupiter that opens an enormous scientific door. All within the framework of known physics, without fiction and without extraordinary assumptions, only an exercise like this as a tool to explore the universe more deeply. In this hypothetical scenario, scientific interest does not arise from an extraordinary announcement, but from a mathematical coincidence that challenges the ordinary. When an interstellar object enters the solar system, its trajectory is usually simple to describe: an open curve, a brief passage near the Sun, and a definitive exit toward deep space. But in this theoretical story, new measurements reveal something that surprises even the most experienced astronomers: an orbital refinement that suggests a statistically improbable alignment with the region dominated by Jupiter. This is not a real prediction or an observed calculation, but a window to understand how numbers govern celestial movements. The scientific question that arises is obvious. How improbable would it be for a visitor from another star to pass so close to the influence of the largest planet in the solar system without any kind of external intervention? To understand that improbability, let us first imagine how an orbit is calculated. Every night, telescopes around the world capture images of the object. Its position shifts slightly in the sky, and those changes feed equations that describe its three-dimensional motion. When the object is very far away, the errors are large. As it approaches, the margins shrink. In this hypothesis, as 3I Atlas crosses the inner solar system, the models begin to show that if the gas jets produce a small but sustained acceleration, its trajectory could project toward a region close to Jupiter. This idea does not imply intention or conscious direction, but an extreme concatenation of physical conditions. Real comets have already shown non-gravitational accelerations on multiple occasions, so the scientific challenge lies in quantifying that behavior within a limiting scenario. In our theoretical exercise, the number that appears in the simulations is surprising, a probability close to 0.4% that an interstellar object with similar initial parameters would end up on a trajectory so close to Jupiter's gravitational domain. This value is not a real measure, but an example constructed to show how scientists analyze the rarity of certain events. The low probability does not imply that something mysterious is happening. It simply reflects how vast and unpredictable the cosmos can be when millions of variables interact. For astronomers, an event so improbable would be an extraordinary opportunity, not a cause for alarm, because it would reveal a dynamic configuration that could rarely be studied with such clarity. This exercise also allows us to explain how the forces that modify an object's orbit work. The gravity of the Sun dominates the movement of 3I Atlas, but as it approaches, the sublimation of ice generates jets of material that act like small natural engines. The orientation, intensity, and duration of these jets determine whether the trajectory deviates a little to one side or the other. In most cases, these accelerations are random, but in this hypothetical scenario, the scientific question arises. What would happen if, within the limits of real physics, a pattern of gas expulsion were persistent enough to create an accumulated deviation that pointed toward Jupiter? The possibility does not contradict any physical principle. It is simply an extreme coincidence. As the hypothetical trajectory is refined, the researchers in the scenario begin to wonder what kind of interaction could arise between an interstellar object and the region near Jupiter. The Jovian giant is a colossal gravitational machine. Its mass is so great that it affects even objects that pass millions of kilometers away. Mathematics leaves no room for doubt. If something approaches closely enough, its speed changes, its path curves, and its orbital energy transforms. All of this is perfectly real, a fundamental part of celestial mechanics. That is why, in this exercise, the alignment with Jupiter becomes fascinating from a scientific point of view. An impact or an extreme approach is not needed to generate interesting phenomena. A dynamic coincidence in the right place is enough. The mathematical analysis also opens the door to studying something that often goes unnoticed: the difference between gravitational capture and gravitational assist. Capture occurs when an object loses enough energy to remain temporarily in orbit. Gravitational assist, on the other hand, is a natural impulse caused by the planet's gravity that accelerates and deflects the visitor. In this hypothetical story, scientists wonder how an interstellar object would respond if it entered the zone where these two possibilities compete. Real mathematics shows that the conditions necessary for capture are strict, but not impossible if the object's speed, entry angle, and jet force align precisely. Although this encounter does not exist in reality, studying it allows us to understand why Jupiter has been a key piece in the evolution of the solar system, deflecting, scattering, and trapping material for billions of years. The question that guides this part 2 is simple and powerful. What does such an improbable alignment reveal about the physics of the cosmos? The answer is that even the most extreme scenarios can arise from natural combinations of events. Mathematics does not discriminate between the common and the extraordinary, it only calculates. That is why this exercise, and yes, helps us understand the fragility of our predictions, the sensitivity of trajectories, and the depth of the processes that shape the movement of interstellar objects. We are not seeking definitive answers, but a rigorous exploration of how the universe would behave under limiting conditions that are completely possible within science. In this hypothetical scenario, the most intriguing aspect is not the orbital coincidence, but the physical behavior of the object. Ordinary comets, even the most unusual ones, follow relatively known patterns when they approach the Sun. Their ice heats up, gas is released in all directions, the activity is chaotic, unpredictable, and dominated by the temperature of each region of the surface. However, the theoretical possibility that an interstellar visitor might show a different pattern opens an exceptional scientific opportunity. In this exercise, 3I Atlas does not behave like a typical first-passage comet, but like a body whose physical behavior reveals characteristics that are difficult to ignore from a scientific point of view. The process begins with sublimation. When the object enters the inner solar system, solar radiation strikes its surface for the first time after millions of years wandering in absolute cold. The ice turns into gas, releasing explosively. In most comets, this expulsion occurs in random directions, depending on the internal structure of the nucleus and which areas receive more light. But in our theoretical scenario, observations show a slightly sustained pattern, as if the jets emerge from regions that activate more persistently than usual. This is not about assuming anything extraordinary, but about exploring the physical limit of how an interstellar body with an unbalanced composition or an internal heat distribution different from that of local comets might behave. The central idea is scientific. If the jets tend to form repeatedly in the same region, with roughly the same orientation, even with natural variations, the resulting acceleration could become measurable. It would not be a large impulse, but enough for the trajectory to tilt slightly toward a new direction over a long period. This possibility has been documented in solar system comets, where small accumulated impulses constantly change orbits. In this hypothetical scenario, that extreme behavior would fit within real physics, allowing a statistically rare approach toward Jupiter without the need to resort to fictional assumptions. One of the most interesting aspects appears in the composition. The ratio between carbon dioxide and water vapor is fundamental to understanding the thermal history of any icy body. In several real comets, unusually high proportions of carbon dioxide have been detected, indicating that they formed in extremely cold regions far from any star. In this scenario, we imagine that 3I Atlas presents an unusually high proportion, which would explain why its jets are more energetic or more persistent in certain areas. This type of exotic chemistry has been observed before. It does not contradict any scientific model, it simply represents an extreme of the natural diversity that exists in icy objects. That chemical diversity is what allows a hypothetical scenario like this to have scientific grounding, even though it does not exist in reality. As activity increases, the scientific community in the scenario begins to note another detail: the possible presence of volatile nickel detected through remote spectra. In reality, telescopes like the Very Large Telescope have already found atomic nickel in common comets, a surprising discovery that opened debates about its origin. In this exercise, the hypothetical detection of nickel without a comparable fraction of iron raises questions about little understood physical processes. It does not imply artificiality, but it does suggest that the object might have formed under very different conditions from those of our solar system. The presence of volatile nickel is a real phenomenon documented in modern astronomy, and using it in an extreme scenario serves to illustrate how scientists reconstruct a body's history from its chemistry. As the object approaches the Sun and its activity intensifies, the way the coma expands also becomes a key point in this hypothesis. The direction of the gas can change the mass distribution around the object, slightly affecting its movement. Detailed observation of these variations allows non-gravitational acceleration to be measured more precisely. This type of analysis is essential for any interstellar visitor, since scientists seek to understand how the materials trapped inside respond to heat for the first time after eons. In a scenario where the path mathematically coincides with Jupiter, every small change in activity becomes worthy of deep analysis. Here a central element of scientific suspense emerges. An interstellar visitor that does not behave completely randomly is in itself a natural laboratory. It does not need to do anything extraordinary to attract attention. It is enough for its activity to be persistent enough to alter its route in a measurable degree. The simulations in this imagined scenario show that even a slight repeated acceleration over weeks would be sufficient to slowly tilt the object's path toward a region near the Jovian giant. Not because the body is aiming, but because physics allows accumulated impulses to produce an unusual but completely possible deviation within orbital mechanics. Scientific interest multiplies for another reason. Interstellar objects are extremely rare. Every time one passes through the solar system, it brings information about its place of origin, the composition of its coma, the way it releases gas, the manner in which it fragments or maintains its integrity. Everything contributes to reconstructing its history. In this hypothetical scenario, a visitor that shows prolonged activity, atypical chemistry, and sustained deviations becomes an incomparable opportunity to study the processes that govern the evolution of bodies from other stars. Even without a real approach to Jupiter, that behavior alone would be enough to justify intensive follow-up. The most notable thing about this exercise is that every detail is supported by real science. Nothing here contradicts the laws of physics or modern models of dynamics and cometary chemistry. What we do is push those laws to their limit, exploring how an interstellar object would react if all the variables aligned in an extraordinary way. The result is a story guided by science, governed by uncertainty, and wrapped in completely natural suspense. We are not seeking definitive answers, but clarity about how the universe operates when coincidences reach a level that we can rarely observe. In this hypothetical scenario where the refined trajectory of an interstellar visitor appears to coincide with the region dominated by Jupiter, a deeply intriguing scientific dimension emerges: the role of the gas giant as a system within another system, a small universe surrounded by moons that in many respects seem more promising for life than Mars itself. In this exercise, the orbital coincidence is not interpreted as a message or intention, but as a starting point to examine how the interaction would work between an interstellar body and a set of worlds that already represent some of the most fascinating environments in all of astrobiology. The surprising thing is not imagining an encounter, but understanding what science reveals when we analyze what could happen if the visitor's trajectory aligned, even if only mathematically, with the gravitational domain of the most massive planet in the solar system. Jupiter is not just a gas giant. It is a gravitational machine that alters routes, fragments comets, temporarily captures material, and scatters particles toward regions where the solar wind does not reach with the same force. Its presence organizes everything around it, creating a dynamic equilibrium that in many ways is as complex as that of a small stellar system. When we pose this scenario, and yes, the first thing that appears is a clear scientific perspective. A statistical approach, even if not extreme, would allow us to study how an interstellar object interacts with that enormous invisible structure that is the Jovian magnetosphere, a magnetic field so large that it could enclose the entire Earth within it. This environment is a natural laboratory where energetic particles, charged dust, organic molecules, and vaporized ice follow trajectories unrivaled anywhere else in the solar system. Interest intensifies when the oceanic moons come into play. Among them all, Europa has for years been the focus of the greatest scientific speculation, not because of supposed signals, but because of its fully verified characteristics. A young ice crust, active cracks, exchange between surface and interior, and beneath it all, a global ocean in direct contact with a rocky floor. That simple contact is enough to allow hydrothermal chemistry, one of the most studied pathways to understanding how pre-biological processes can arise. In this hypothetical scenario, an interstellar visitor passing near Jupiter's gravitational domain could release through its jets microscopic fragments that would end up temporarily trapped in the magnetosphere and finally fall slowly onto Europa's surface. It would not be an impact nor a massive deposit, but a natural process that already occurs with other comets and could be repeated in this extreme case. Ganymede offers a different but equally fascinating scenario. It is the only moon with its own magnetic field, creating a bubble within Jupiter's bubble. In a hypothetical approach, any material entering that region could behave completely differently than on Europa. Ganymede's internal layers with stacked oceans suggest a structure where organic compounds could remain trapped for thousands of years before any internal process transports them inward. This complexity makes Ganymede an ideal target for studying how different magnetic fields interact with charged particles from an interstellar object. Callisto, on the other hand, represents the opposite extreme. Its surface is the oldest among the large moons, full of craters unchanged for billions of years. Its deep ocean, isolated by a thick, cold layer of ice, is an environment totally distinct from that of Europa and Ganymede. In this scenario, any material deposited on Callisto would remain almost intact, frozen in place as if it were a natural archive. This quality is what makes Callisto an exceptional candidate for studying how interstellar organic material could be preserved without being altered by internal processes. Thus, even in a hypothetical story, science finds real paths to explore. The interaction would not occur directly, but through natural processes. When an interstellar visitor releases particles, they become incorporated into the flow of dust and plasma circulating around Jupiter. The magnetosphere acts as a cosmic distributor, channeling material towards specific regions depending on the electrical charge and speed of each particle. In real life, this phenomenon is responsible for the coloration of some regions of the moons and for temporary changes in their extremely thin atmospheres. In our exercise, the visitor's behavior has no intention, but the mathematical coincidence would allow us to study in real time how that material is incorporated into such a dynamic system. However, what generates suspense in this scenario is not the possibility of interaction, but the extraordinary scientific opportunity it would offer. An interstellar object loaded with chemistry formed around another star approaching the most promising natural laboratories in the solar system. The hypothesis opens a bridge between two areas of study that can rarely be connected: the primitive composition of outer worlds and environments capable of sustaining liquid water beneath ice. Science does not need fiction to awaken wonder. The simple act of imagining this coincidence already reveals how much we still do not know about the evolution of icy worlds. The key is that this scenario, although extreme, is sustained within known physics. It does not require altering natural laws or inventing exotic behaviors. It is enough to consider that on very rare occasions the universe allows two improbable events to coincide: an active interstellar visitor and a planetary system with oceanic environments. When those variables come together, even if only in a theoretical simulation, science fills with questions that deserve to be explored. This analysis does not seek to present a destiny or intention, but to reveal that a mathematically close encounter would allow us to study how two completely distinct stories behave together: that of a body traveling from another star and that of a Jovian system that has shaped its moons for billions of years. In a universe governed by celestial mechanics, even the most improbable coincidence can open a window to the past and the future at the same time. In this hypothetical scenario where 3 Atlas appears to be heading, by pure mathematical coincidence, toward the region dominated by Jupiter, a detail emerges that completely transforms scientific interest: time. Interstellar objects do not wait, do not slow down so that humans can study them calmly. They do not stop to allow telescopes to collect all possible data. In reality, they cross the solar system like silent bullets, visible for only a few months before being lost forever in the darkness. In this exercise, this limitation becomes a critical element. If the visitor followed a route that brought it significantly closer to the Jovian giant toward March 2026, the scientific community would have less than 9 months to coordinate observations, adjust instruments, and make decisions that under normal circumstances would take years. The magnitude of the challenge begins to reveal itself when the object's speed is compared to the normal pace of research. From Earth, each observatory has a reduced margin to capture clear images. The visitor's brightness could vary dramatically as it approaches the Sun. Activity could increase or decrease depending on the amount of exposed ice. And any sudden fragmentation would alter the entire hypothetical trajectory. In this theoretical scenario, scientists know that uncertainty grows as the time window narrows, not because there is danger, but because every lost minute represents data that can never be recovered. The next critical point in this exploration is the discussion about the use of spacecraft already present in the solar system. In real life, Juno orbits Jupiter collecting information about the atmosphere, the magnetosphere, and the planet's internal structure. However, Juno is not designed to perform emergency maneuvers to intercept an interstellar object. Its fuel is limited, its instruments were calibrated for specific objectives, and its orbit responds to a carefully structured scientific plan. In this hypothetical exercise, astronomers debate whether it would be possible to slightly divert the spacecraft's route to observe the visitor from a unique angle that no ground-based telescope could provide. The discussion would be intense not because of risk, but because a small deviation could compromise years of planned objectives. The question that dominates the tension is not whether they should do it, but what they would sacrifice in exchange. At the same time, the JUICE spacecraft, sent by the European Space Agency, is slowly heading toward the Jovian system on its authentic mission to study Europa, Ganymede, and Callisto. Its real arrival is scheduled for 2031, too late to participate in an encounter with an interstellar visitor in 2026. In this hypothetical scenario, scientists reflect on how much could be revealed if a spacecraft of that type were already in orbit. This scientific frustration illustrates the need for something often mentioned but rarely discussed with sufficient urgency: the importance of developing rapid response systems capable of studying interstellar objects when they appear before they disappear forever. From a scientific point of view, the temporal limitation also forces prioritization of what type of data would be most valuable. Should the focus be on the chemical composition of the visitor, on how its activity changes with distance from the Sun, on its possible interaction with the solar wind? Or would it be better to concentrate resources on dynamic simulations that explore how it would behave in its hypothetical approach to Jupiter? In a scenario where the trajectory appears to converge toward a region of extreme scientific interest, every decision becomes critical. There is no time to repeat experiments or wait for better instruments. Science must act quickly, precisely, and with global coordination that has rarely been achieved. Pressure increases as the hypothetical minimum distance between the visitor and Jupiter is calculated. An approach of tens of millions of kilometers seems enormous from a human perspective, But in orbital dynamics, that separation can produce significant alterations in speed, rotation, and object activity. The astronomers in the theoretical scenario know that even a relatively distant encounter could produce extraordinary data, especially if the jets increase in intensity during the approach. Cometary activity is unpredictable. A sudden increase in solar heating could trigger a gas explosion that would send particles in different directions, some of which could end up temporarily trapped in the Jovian magnetosphere. Documenting that process would be a direct window into phenomena that normally cannot be observed. Another key element in this hypothesis is uncertainty about the stability of the visitor's nucleus. Interstellar objects are fragile. Oumuamua, although small, showed unexpected changes in its movement. Borisov partially fragmented during its close passage to the Sun. If 3 Atlas were subjected to intense heating, the possibility of seeing cracks, detachments, or fragmentations would increase with each day. A large fracture could completely alter the mathematical projection toward Jupiter, deflecting it or even dispersing it. This risk is not dangerous for Earth, it is a scientific risk because it would completely change the information the community believed it could obtain. Time becomes the silent antagonist of this hypothetical story. The window is closing not because of destruction but because nature acts without waiting. The real tension arises when the researchers in the scenario realize that the visitor could change its behavior at any moment. If the jets intensify, the mathematical trajectory can tilt. If they decrease, the path can open wider. Every update modifies the scenario. Simulations must be run hundreds of times per week. The slight uncertainty that always accompanies interstellar objects becomes a determining factor. Although there would never be a danger of impact with Earth, the uncertainty about the coincidence with Jupiter's region keeps a powerful scientific question alive. Will it be possible to capture enough data before the object moves forever out of human reach? Science knows that when the window closes, the only thing left is the measurements that were managed to be recovered. In this exercise, astronomers around the world are aware that every hour of observation carries enormous weight. They feel on the edge of an opportunity that may not repeat itself for centuries, to analyze an interstellar visitor that, through an extraordinary combination of factors, could approach a planetary system with oceanic moons. The urgency does not come from fear, but from the longing to understand what the cosmos offers on very rare occasions. Thus, the question that dominates this entire hypothetical exploration becomes increasingly inevitable. Will humanity manage to gather enough data before the visitor's trajectory moves forever beyond human reach? In this hypothetical scenario where 3 Atlas appears to be heading toward the region dominated by Jupiter, the key to understanding everything is not the spectacular nature of a rare approach, but the mathematics that operates beneath every movement. When a body crosses interstellar space, its history is written in the speed it brings, the angle at which it enters the solar system, and the way its surface reacts to solar heat. This is where physics becomes narrative. Every gas jet, every released fragment, every change in solar pressure is a word in a language that astronomers know how to read. And in this exercise, the essential scientific question is, how could those tiny forces, under extreme but possible circumstances, modify the trajectory enough to originate the coincidence with Jupiter? In reality, comets behave like small natural engines when the ice trapped inside heats up, expands, fractures, and is released, pushing the nucleus in the opposite direction. These impulses are so weak that a person would not feel them if standing on the object's surface, but in the vacuum of space where resistance is non-existent, they can accumulate over weeks or months and notably alter the route. In most cases, this activity is chaotic. Jets activate and deactivate, emerge from different cracks, and respond to irregular rotation patterns. However, in this hypothetical scenario, scientific interest arises when the models indicate that the acceleration could be slightly more persistent in one area of the surface, enough to cause a small but sustained deviation. This deviation does not imply intention or control, it is pure physics, a combination of chemical composition, ice distribution, and uneven exposure to sunlight. This is where mathematics becomes crucial. The astronomers in the scenario must introduce extremely sensitive parameters into their simulations. A minimal error in measuring activity can generate completely different predictions. That is why, when this exercise poses a statistically rare alignment with Jupiter, the scientific doubt is legitimate. How can an interstellar object formed in an unknown stellar system end up in a scenario that brushes the limits of probability? The answer lies in the very nature of orbital mechanics. Space is not a static vacuum, it is a set of forces in constant interaction. The solar wind pushes, radiation excites molecules, magnetic fields deflect charged particles, and the sun's gravity acts as the director of an immense choreography. Each of these factors contributes, even if minimally, to the visitor's final route. In this hypothetical exercise, scientists imagine how a persistent jet pattern could act as a natural adjustment, slowly tilting the direction of movement toward a point where months later the curve projects toward the Jovian giant, not because the object is aiming, but because the universe allows coincidences as improbable as they are revealing. As the visitor advances through the inner solar system, its physical characteristics become increasingly important. The size of the nucleus, the density of the ice, the amount of volatile material, and the presence of exotic molecules influence how it responds to heat. In this theoretical scenario, it is observed that the object releases more carbon dioxide than water vapor, a condition possible in bodies formed far from young stars where carbon dioxide remains trapped in greater quantity. This type of composition allows jets to be more powerful or more stable in certain areas, which in turn could reinforce the accumulated deviation. Again, without the need for fiction, science offers enough diversity in cometary chemistry to allow extreme scenarios. Mathematics becomes even more complex when changes in rotation are considered. In comets, jets not only deflect the trajectory, they can also modify the spin period. If rotation changes slightly, new areas of the object are exposed to the sun for longer, heat up faster, and begin to release gas. This natural feedback can create a cascade effect where small variations generate accumulated changes. In this imagined scenario, astronomers around the world would work tirelessly to update the values of rotation, activity, and object orientation. Each update could alter the projection toward Jupiter, increasing or reducing the probability of coincidence. Scientific suspense arises when the trajectory within the mathematical margins remains aligned with the region near the giant. It is not a firm prediction, but a tendency that appears again and again in the simulations. The question that motivates this entire hypothetical investigation is not whether the coincidence will occur, but what it would reveal about interstellar objects if even the most improbable combination could manifest. Nature does not need intention to produce extraordinary alignments. The universe is so vast that somewhere and at some moment, even the most improbable coincidences can occur. This scientific exercise explores one of those extreme possibilities. The scientific implications would be enormous. An interstellar visitor that modified itself notably due to its own activity would allow us to study with rare clarity how internal processes determine an object's fate. Understanding this relationship between activity, rotation, and trajectory is one of the current challenges in comet research. If such a case mathematically coincided with Jupiter's region, even if only in a simulation, it would allow us to explore fundamental questions. How sensitive is the trajectory of an interstellar visitor? What is the real limit of jet influence? What does chemistry reveal about the history of an object formed in a place we will never see? In this section, mathematics becomes the silent protagonist. Everything happens far from human eyes, in regions that no observatory can physically reach. However, every equation reflects the accumulated history of millions of years. Nothing in this hypothesis contradicts science. It simply takes known physical conditions to a limit that is rarely studied. The coincidence with Jupiter is not a signal or a message, but a scenario that reveals how delicate the equilibria guiding interstellar travelers can be. The scientific narrative finds here its most subtle point. When an object's deviation depends on such small forces, the final result becomes a window into the past and future of the universe. In an exercise like this, mathematics does not serve to predict a real event, but to show how an improbable trajectory can become a tool to better understand the natural processes that shape the cosmos. In this hypothetical scenario where 3 Atlas appears to be heading by pure mathematical coincidence toward the region dominated by Jupiter, scientific attention begins to focus on something that often goes unnoticed by the general public: the deep chemistry of an interstellar visitor. If the trajectory attracts attention because of its rarity, the object's composition awakens a different level of scientific unease, not because it suggests something extraordinary, but because it reveals clues about a formation environment completely different from ours. Chemistry is the oldest language in the universe. It predates planets, stars, and any form of life. And in this exercise, that language begins to show phrases that science does not yet know how to read completely. The first thing that stands out is the ratio between carbon dioxide and water. In solar system comets, water vapor usually dominates activity, especially near the sun. However, some real comets have shown unusually high proportions of carbon dioxide, indicating that they formed in extremely cold regions. In this hypothetical scenario, Observations of 3I Atlas reveal an even more extreme proportion where carbon dioxide far exceeds water. This condition explains the more persistent behavior of certain jets, since carbon dioxide sublimates at lower temperatures than water ice. Strong activity even far from the Sun fits perfectly within known physics, but indicates a radically different origin. Chemistry does not tell simple stories. Every molecule is a fragment of pure memory. As the spectra become clearer, another detail appears that puzzles the scientific community within the scenario: the presence of volatile nickel. This finding is not fictional. In real life, atomic nickel has been detected in common comets using European telescopes. But in this exercise, the detail that ignites scientific curiosity is the apparent absence of iron in comparable proportion. In a normal environment, nickel and iron appear together. They are sibling elements formed in similar processes. Seeing one without the other is possible but rare. It does not mean anything extraordinary, but it does suggest that the interstellar visitor could have formed in an unusual chemical environment, perhaps a molecular cloud rich in metal carbonyls or a protoplanetary disk where thermal processes separated elements that normally travel together. This type of exotic composition becomes relevant in the hypothetical scenario because the molecules released in each jet not only alter the trajectory, they also reveal conditions that existed in another stellar system. The scientists in the exercise know that interstellar objects are time capsules. Every volatile element trapped inside is a silent witness to a star that may no longer exist. The presence of unusual compounds does not imply artificiality. On the contrary, it opens a range of completely natural possibilities that show how diverse chemistry can be among the stars. In a sense, studying an object like this would be like reading an ancient manuscript written in an unknown dialect. The most fascinating thing is that as the visitor approaches the Sun, the molecules trapped during its formation begin to be released slowly. In this hypothetical story, chemical activity increases as solar radiation penetrates internal layers that had not been heated for millions of years. One after another, the compounds emerge, reconstructing the object's past. Every spectral line is a message that traveled through interstellar space for inconceivable times. Every variation in intensity reveals a thermal transition that may never repeat itself. What science seeks is not a hidden meaning but pure information. What conditions existed where 3 Atlas formed? How different was that environment from ours? How do these objects contribute to the overall chemistry of the galaxy? The hypothesis of alignment with Jupiter adds a deeper level to this exploration. If the visitor approached even mathematically the domain of the gas giant, some of those molecules could be temporarily incorporated into its magnetosphere, not as a delivery or intentional act, but as a natural consequence of how Jovian plasma captures charged particles. This would allow us to study how interstellar chemistry interacts with a complex planetary environment. Particles that reached the icy moons could become trapped in the surface ice, preserved as chemical traces that in real life we could study through specialized missions. Scientific tension grows when the visitor's activity begins to reveal simple organic molecules. This hypothetical finding breaks no rules. Organic compounds such as formaldehyde, hydrogen cyanide, and carbon-based molecules that serve as fundamental building blocks in prebiotic reactions have already been detected in real comets. In this exercise, the appearance of such compounds feeds a powerful scientific question. How are the basic ingredients of life chemistry distributed throughout the galaxy? This is not about suggesting a purpose, but about understanding the natural flow of organic molecules between stellar systems. Comets, both local and interstellar, may have transported chemical material between distant regions for billions of years. But the most disconcerting and also the most realistic possibility is the detection of molecules whose spectral signature we do not yet understand. In real comets, the unknown fraction of the spectrum is sometimes surprisingly large. In this scenario, the presence of unidentified compounds becomes the heart of scientific suspense. What processes gave rise to those molecules? Under what conditions were they assembled? What story do they tell about the star where the visitor was born? Here science finds itself facing a natural frontier. There are no certainties, only questions guided by real data extended to a theoretical limit. Of all the chemical clues, the most intriguing in the scenario is nickel. In many real biochemical processes, nickel acts as a catalyst. It forms part of essential enzymes in organisms that inhabit extreme places, even on Earth. This does not mean that there is a direct connection with biology in an interstellar object. It simply implies that nickel has properties that help accelerate chemical reactions. In a hypothetical approach with Jupiter, The incorporation of nickel into the environment of its oceanic moons would allow us to study how this metal interacts with salty water subjected to internal heat generated by tidal forces. That combination does not require imagination. It is real on Europa and Ganymede. Suspense does not arise from the possibility of life, but from the depth of the questions the interstellar visitor poses. Every molecule released from its surface would be another piece of the galactic puzzle that science has been trying to solve for decades. In a scenario where time is limited and the trajectory appears to head toward a natural laboratory as complex as the Jovian system, urgency combines with humility. Direct access has never been had to the chemistry of a world formed under another star. Every spectrum, every chemical line, every faint signal represents an opportunity that may never repeat itself. The chemistry that should not exist is not the one that contradicts the laws of physics, but the one that challenges our expectations. In this hypothetical exercise, 3 Atlas does not seek a destination. It only reveals through its composition that the universe is infinitely more diverse than we imagine. Science moves along that frontier trying to decipher what the visitor brings from a place we will never know. In this hypothetical scenario where the refined trajectory of 3I Atlas appears to align by pure mathematical coincidence with Jupiter's gravitational region, scientific attention shifts toward a set of worlds that were already mysterious before this interstellar visitor entered the scene. Among all the bodies in the solar system, Jupiter's icy moons occupy an extraordinary place. It is no coincidence. Each one hosts conditions that, although different from one another, turn the Jovian system into a kind of natural laboratory where geological, chemical, and energetic processes develop that are not found anywhere else near Earth. In this exercise, the supposed approach of the visitor does not imply direct interaction, but it does open an exceptional hypothetical opportunity to wonder how these worlds would react if interstellar particles reached their environment. Europa, the most famous of the oceanic moons, is a perfect example of why science already considers Jupiter a system with astrobiological potential. Its young ice crust shows active fractures, areas where the interior seems to push material toward the surface, and regions where interaction between the ocean and the outer layer is evident. This is not speculation. Missions like Galileo have collected data confirming the existence of a global ocean beneath the ice. In this scenario, and yes, astronomers imagine how small amounts of material released by an interstellar visitor could become trapped in the particle flow lines surrounding the moon. It would not be a dramatic process. Instead, it would be a natural, slow, almost delicate mechanism where microscopic grains travel between magnetic fields, deposit on the surface ice, and become sealed under new layers as the moon renews itself. If there were ever the opportunity to compare interstellar chemistry with oceanic chemistry, even indirectly, Europa would be the best place to observe it. Ganymede presents a completely different scenario, though equally captivating. This world is so large that it surpasses Mercury in size, but unlike any other satellite, it possesses its own magnetic field. This creates a mini-environment within the Jovian environment, a space where charged particles follow unique trajectories before falling onto the surface. In our hypothetical exercise, scientists wonder how that magnetic field would react if it received particles from an interstellar object. The dynamics would be complex. Some particles could remain trapped for long periods, others could precipitate toward the surface generating temporary spectral signals, and a small number might mix with the ice covering the upper layers of the satellite. Ganymede is not simply a moon, it is an environment where electromagnetic, gravitational, and thermal forces intertwine in a delicate equilibrium. An interstellar visitor approaching, even without direct interaction, would serve as a unique opportunity to study how this world responds to such strange external stimuli. Callisto, in contrast, represents frozen stillness. Its surface is so ancient that it practically preserves intact the history of the solar system. The visible scars on its icy crust do not erase, do not renew, do not change frequently. It is a natural archive, a book with hard pages where every impact, every dust deposit, every fragment falling from space is preserved for millions or even billions of years. In this hypothetical scenario, interstellar particles reaching Callisto would remain on the surface unaltered, as if the satellite were an ice museum capable of storing traces of the visitor forever. For science, this idea would be fascinating because it would offer the possibility of analyzing interstellar chemistry preserved in an almost pure state. There would be no intense internal processes, no volcanism, no ice renewal. Callisto would be the equivalent of a natural capsule that preserves every grain of dust that touches its surface. Beyond the icy surfaces, the Jovian system offers an even more complex environment. its immense magnetosphere. This magnetic field is so large that if it were visible to the naked eye, it would cover a much larger area of the sky than the full moon. The scientists in the hypothetical scenario know that any particle entering this region experiences forces that redirect, accelerate, or deflect it according to its electrical charge. In an imagined extreme approach, used only as a model, part of the material released by the interstellar visitor could become temporarily trapped in the Jovian radiation belt. That material would travel in spirals, forming complex trajectories before precipitating toward one of the moon's or the planet's upper atmosphere. This phenomenon already occurs with other comets that approach Jupiter, and extending it to an interstellar object in a theoretical exercise offers a window to understand how different particle populations mix in the Jovian environment. Scientific suspense grows when it is considered that under hypothetical circumstances the interaction between interstellar particles and oceanic moons could be detected by instruments designed to measure surface composition. Europa Clipper, for example, in real life will directly study Europa's ice in the next decade. If an extreme coincidence like the one posed in this story occurred, even without direct interaction, the collected data would reveal additional signals related to grains from interstellar space. That type of detection would be revolutionary not because of its impact but because of its scientific value. It would allow, for the first time, a comparison of material formed around another star with oceanic environments within our own solar system. Jupiter itself also plays a crucial role in this scenario. Its deep atmosphere, formed by hydrogen, helium, and traces of other elements, acts as a natural filter that absorbs and transforms any particle that falls into it. If the interstellar visitor approached closely enough, even a simple change in dust distribution around the planet would generate temporary alterations in the reflectivity of some high atmospheric zones. It would not be an event visible to the naked eye, but it would be detectable by specialized instruments. Jupiter's atmosphere is a cauldron in constant motion. Every current, every turbulence, every band, and every storm can act as a temporary trap for dust grains. Studying how that environment responds to interstellar material would be like observing a natural experiment executed on a gigantic scale. In this scenario, and yes, nothing requires imagining phenomena outside known physical reality. Jupiter's icy moons are already extraordinarily complex environments in themselves. Europa reveals evidence of recent activity and potential chemical exchange between ocean and surface. Ganymede possesses a magnetic field that defies expectations for any body of its size. Callisto preserves cosmic history on its intact surface. Each one contributes something different to scientific exploration. An interstellar visitor approaching this system would be like a page torn from a book written under another star that accidentally falls among three worlds with unique conditions. There is no richer narrative than that. In the end, the question guiding this section of the hypothetical scenario is not whether the visitor would significantly alter these worlds, but what science could learn by observing how this diverse system reacts to such a strange external stimulus. In a universe where improbable coincidences occur naturally, Jupiter and its moons offer a perfect setting to study the interaction between interstellar chemistry and environments capable of sustaining liquid water. The coincidence is theoretical, but the science behind it is real. The true importance of this exercise is not an encounter, but the understanding that arises from imagining how one of the most complex planetary systems would respond to a visitor carrying the memory of another corner of the galaxy. In this hypothetical scenario in which the refined trajectory of 3 Atlas appears to coincide mathematically with the region governed by Jupiter, science continues to move within its natural limits, exploring every possibility without abandoning the rigor that characterizes it. However, there is a point where even the most cautious researchers pause before speaking completely freely, not because they fear the public, but because certain questions, although perfectly valid within the theoretical realm, require special tact. This is the territory where scientific speculation must remain strictly separate from imagination. Here a question arises that no one wants to state openly, although its presence is inevitable when extreme coincidences are studied. How far can science go in analyzing an improbable scenario without crossing the line into the extraordinary? In this exercise, and yes, the hypothesis is not that the interstellar object has a purpose or follows a plan. That type of interpretation has no place in physics. The question is different. What can we learn if we analyze with full scientific honesty what kind of natural processes could give rise to such an uncommon pattern? Nature offers coincidences that at first glance seem impossible. Planetary trajectories, orbital resonances, gravitational encounters, chemical chains that form in extreme environments. All of this demonstrates that the universe does not need intention to produce results that appear carefully designed. In this section, science delves into the paradox. Improbability is not evidence of anything more than the immeasurable size of the cosmos. Despite this, a topic inevitably appears in every scientific conversation that touches the limits of the unknown: panspermia, not as an assertion, but as a historical hypothesis that has accompanied astronomy for more than a century. In its most serious version, panspermia is the idea that complex organic molecules and potentially chemical precursors of life can travel from one stellar system to another embedded inside comets, asteroids, or interstellar dust. This hypothesis does not propose intentionality, but a natural, almost incidental process where chemistry moves through the galaxy long before life exists on any world. In this exercise, if an interstellar visitor approached Jupiter, even mathematically, scientists would consider the possibility of studying whether some of its compounds could be temporarily incorporated into the magnetosphere or the icy surfaces of its moons. It would not be a message or a signal, it would simply be interstellar chemical flow finding a new environment to interact with. What produces suspense in this section is not the idea of life or the assumption of engineering, but the scientific silence around questions that require extreme caution. When an interstellar object brings unusual compounds, unexpected proportions of volatile materials, and a trajectory that in a purely theoretical framework could approach a planetary system with subsurface oceans, the public imagination tends to run faster than the data. That is why the scientists in the scenario focus exclusively on what can be measured, observed, or modeled. Everything else remains outside. Science does not advance with extraordinary assumptions. It advances with data that reveal patterns, even if those patterns seem improbable. Within this exercise, another reflection emerges: the comparison between what is observed in interstellar objects and what is known about the origins of life on Earth. On our own planet, many scientists believe that part of the primordial organic material arrived through impacts of comets and asteroids during the early intense bombardment. That rain of cosmic debris could have deposited amino acids, simple organic molecules, and other compounds that contributed to prebiotic chemistry. Nothing in that story requires purpose. It only requires time, collisions, chemistry, and heat. In this scenario, if 3I Atlas passed relatively close to the Jovian system, although only a mathematical encounter, it could offer an additional example of how interstellar material can interact with worlds that possess hidden oceans beneath their surface. This theory, known as natural panspermia, is solid enough to be studied, but too broad to be easily demonstrated. In this section, science maintains a prudent distance. It is not claimed that the visitor carries life. The question is whether its hypothetical approach would allow us to observe how interstellar material behaves in an environment where liquid water exists beneath layers of ice. That alone would be a monumental discovery, an opportunity to observe, even in model form, how the chemistry of two distinct worlds, one local and one interstellar, briefly converge. The question that no one wants to voice openly then appears under a completely scientific light: how does human uncertainty affect our interpretation of cosmic coincidences? The answer is simple and profound: science must remain neutral. Astronomers can only evaluate what they can measure. Coincidences, no matter how improbable, must not be interpreted as messages. They are mathematical windows through which we can see the functioning of the universe more clearly. In this scenario, 3I Atlas is not a messenger. It is a traveler whose story is told solely with chemistry, movement, light, and gravity. The final layer of suspense arises when the hypothetical scenario intersects with one of humanity's oldest questions. If life exists elsewhere, how do its ingredients travel between worlds? Although this exercise does not attempt to answer that question, it does show that extremely rare events could serve as models to understand that chemical flow which essentially recognizes no stellar boundaries. Chemistry does not obey any intention. It simply travels, struck by radiation, altered by extreme cold, trapped in ice for millions of years, and released again by a ray of sunlight. In a universe where silence is the norm and life is a phenomenon not yet confirmed beyond Earth, even a hypothetical scenario like this can teach us something valuable, not about messages but about processes, not about signals but about natural patterns, not about intentions, but about coincidences so improbable that exploring them reveals the profound complexity of the cosmos. In this hypothetical scenario where the refined trajectory of 3I Atlas appears to align mathematically with the region dominated by Jupiter, the scientific story advances toward a decisive moment. Here it is no longer only about discussing the hidden chemistry in the visitor, nor about analyzing the behavior of its jets, nor about studying how internal activity modifies its course. At this stage, the attention of the scientific community concentrates on a crucial point that can occur within the real limits of physics when an interstellar object passes through a zone where the gravitational influence of the gas giant is strong enough to slightly modify its movement without requiring an extreme approach. This is the space where calculated scenarios are born. Possible trajectories, minimal deflections, distant encounters, and subtle transformations that can produce detectable signals. At the heart of this hypothetical investigation are three mathematical scenarios that require no fiction, only calculations. The first is the simplest, a clean passage. In this possibility, the interstellar visitor crosses the outer region of the Jovian domain, experiences a slight alteration in its speed, and continues its journey toward interstellar space. This outcome is the most likely in most real astronomical analyses. Even a moderate approach could generate a smooth curvature in the trajectory, a kind of gravitational greeting between two worlds that will never meet again. The interesting thing is that in this model that deflection could allow the internal activity of the object to be measured more precisely, because changes in its speed would reveal the balance between gravitational force and cometary jets. The second mathematical scenario is more complex, a temporary resonance. In this hypothetical case, the interstellar visitor is not captured, but it does remain for a longer period within Jupiter's zone of gravitational influence. This is not a stable orbit or a lasting bond, but a brief dance where the object performs one or two gentle turns before escaping again into the void. This type of resonance has been observed in long-period comets within the solar system. In this theoretical story, scientific interest lies in studying how that temporary permanence could allow greater amounts of material driven by the jets to be distributed within the magnetosphere. Each partial turn generates a distinct chemical record, a signature that mixes with the giant's magnetic environment and that could be detected through specialized observations. The third scenario, equally realistic within theoretical limits, is fragmentation. Comets, especially those experiencing their first approach to the Sun in millions of years, are fragile. Internal activity, extreme heating, and rotation can generate stresses that exceed the structural capacity of the nucleus. In this exercise, the mathematical possibility of a partial rupture is not an element of drama, but a natural physical consequence. If 3I Atlas fragmented into several pieces, the hypothetical trajectory toward Jupiter's region would change. Some fragments could deviate widely, others could follow a similar route, and a small number might temporarily enter the magnetosphere or even precipitate particles toward the icy moons. Again, all of this is part of processes already observed in real comets. The difference is that here we analyze how those events would interact with an environment as dynamic as the Jovian system. While these scenarios are calculated mathematically, science prepares to observe all possible signs. The object's brightness could increase or decrease depending on the intensity of sublimation. The shape of the coma could become asymmetric, indicating the predominant direction of the jets. The tails could separate into multiple structures, a common phenomenon when escaped particles follow different paths according to their size and electrical charge. Even rotation could accelerate slightly, causing changes in the periodicity of reflected light. Each of these signs would be a window of information about the internal state of the interstellar visitor, and the scientific community would study them with a mixture of urgency and wonder. Instruments on Earth, even the most powerful, cannot achieve the precision that a spacecraft could offer. But in this hypothetical scenario, humanity has no spacecraft close enough to Jupiter to observe the encounter in detail. This limitation creates natural suspense. Astronomers know they depend on remote telescopes, the solar wind, light patterns, and numerical models. Each observatory contributes a different piece of the puzzle. Some focus on chemistry, others on dynamics, others on thermal evolution. The interstellar visitor temporarily becomes the most fascinating object in the solar system, not because it represents danger, but because its mathematical coincidence with such a complex world is a unique opportunity to study natural processes that can rarely be observed. Scientific tension grows as the object approaches the point where uncertainty reaches its maximum. The projected trajectory, even in a purely theoretical scenario, could change with any sudden increase in activity. An unexpected jet could alter the exit angle. A previously inactive zone could begin to sublimate, generating an impulse oriented opposite to what was calculated. The astronomers in the hypothetical exercise know that although mathematics allows possible scenarios to be projected, nature remains unpredictable. The question that permeates this entire analysis is not what will happen, But what signals can be captured before the visitor permanently leaves the region dominated by Jupiter? The most interesting thing about this scientific exercise is that without resorting to fiction, each scenario opens a window to a fundamental aspect of the universe. A clean passage reveals the sensitivity of interstellar orbits. A temporary resonance shows the complexity of gravitational interactions. A fragmentation offers a unique view of the internal structure and thermal evolution of the object. None of these outcomes requires intentionality or purpose. They are simply the natural consequences of physics when an interstellar traveler comes into contact, even from a distance, with one of the most complex planetary systems we know. As this section of the hypothetical investigation ends, it becomes evident that science and uncertainty coexist inseparably. The signs that astronomers seek are not messages but patterns. They do not announce a destination, but a story written in dust, ice, and light. The interstellar visitor, silent and distant, continues its path without knowing that in scientific imagination it has provoked one of the most detailed investigations that could be conceived.